Hey guys, Mr. Canistero here. In today's video, we're going to talk about modeling energy conservation. So we're going to be using the law of conservation of energy to figure out where energy goes in a variety of situations. So as you're watching the video today, you'll know that you really understand what's going on if by the end you can say, you know what, I can use energy conservation and these things called LOL charts to model how energy transforms in really any physical situation. So if you can make up a situation and then use the chart to model how energy transforms from one form into another, you really kind of understood this video. Before we get started though, let's do a quick little recall just to kind of remind ourselves with what we're talking about. So we're going to be talking about the law of energy conservation, and in its barest, most kind of broken down form, we know it's written as energy can't be created nor destroyed. So energy can't be created or nor destroyed. Another way I like to think about it, though, is if energy can't be created and destroyed, but it does change forms from one form into another. So if you measure the total energy of a system, the total energy of a closed system stays constant. Now, why do we say a closed system? Because if, depending on how I specify my system, we could lose energy. For example, if energy is lost to heat, we would say energy is lost. So we're going to really specify that closed system is constant. Awesome. So what does energy do? Even though the total energy stays constant in a closed system, we know that energy will change from many forms into many other forms. So what are some of the common ones that we've seen? Well, if I have a ball and I take it and I throw it, for example, that has moving energy. And what we call moving energy, we call that kinetic energy. As a symbol, we typically call it Ke for kinetic energy. Oftentimes in LOL charts, you'll see it written as E with a subscript K, EK. What are some aspects we know about it? We know that the formula for kinetic energy is represented by the equation kinetic energy is half the mass of the object times its velocity squared. And really that key part about kinetic energy, it really depends on the speed of an object. Another one we've talked about is the gravitational potential energy of an object. And that's really an energy associated with being with a position. For example, if I have some ball on the ground at rest, and then I do work to lift it up some set height or some set distance, we say that that ball has energy stored in it because as soon as I release it, it's going to begin to fall towards the ground and it's going to have kinetic energy. And so due to its position, we say that it possesses some kind of a stored energy, and we call that gravitational potential energy. As letters, we often call it potential energy with a subscript G. That's the most often one you're going to see. And you can solve for it by doing mass of the object times the acceleration due to gravity times the height in the air. And really for this one, the big factor is the height. Another commonly seen energy that we've discussed is the spring or elastic potential energy stored in an object. And that one, which we talked about in class, is equal to 1/2 times the spring constant times the stretch of the spring squared. So when I take a spring and I either compress it or I stretch it by a certain amount, I have to do work in order to stretch it or compress it. And when I do work, I store energy in that spring. For example, like the popper toppers that we all know and love far, far too much in class. When that popper topper pops, that elastic potential energy is converted into kinetic energy, which propels it upwards in the air. Now, in addition to these common forms, which, by the way, the two potential energies and the kinetic energy, we often call mechanical energy. There are many other forms of energy that we can discuss. Most of the time, we're not going to go into these too much in physics, but they're really, really worth knowing. All of them, though, are going to be lumped up under the term Q, and Q is typically called internal energy. Now, when you see the word internal energy, you should be really thinking things like heat, sound, energy loss to friction, and the like. If for some reason you see a system appearing as though it's losing energy, for example, you throw a ball in the air and all of a sudden it begins to slow down, but not all the energy is going in the gravitational potential, well, you know air resistance is happening. Q represents, the energy lost to air resistance. Or if you have those two giant metal clacker balls that hit each other and burn a hole through paper, like that, where their kinetic energy is converted to heat, and the heat burns a hole through the paper, that's that Q again. And so internal energy, we typically really refer to it as the energy lost to heat and friction. Other types of energy to consider, there is light energy, and light energy typically falls under the category of electromagnetic energy. Now, we haven't talked about this one yet, but because light is part of what's called the electromagnetic spectrum, or light is electromagnetic radiation, we refer to light energy as electromagnetic energy. Finally, one more worth discussing today. There's another type of energy called nuclear energy, and nuclear energy is really the energy stored in the atom of any in the nucleus of any atom. So when you think nuclear energy, you really should be thinking atomic bombs like fission and fusion. So our goal for energy conservation is we're going to use all these types of energy that we just talked about and examine how does energy transform from one form into another. And so there are many other ways of doing it. There are many, we have all these equations that we can just set equations equal to each other. But the first way I like to teach is starting with what's called a LOL, or an LOL chart. And the reason why it's called LOL is you put a graph on one side of the paper, you have a system which you represent as a circle that represents as a closed system, and then another graph. And kind of looking at it from far away, you can see it looks like LOL. And all we're going to do is we're going to use a bar chart to say what energy a system starts with, what the system is in the direction of energy flow, and then where the energy is at the end. And it's just purely a qualitative way of reasoning what types of energy we have. So when you throw a ball up into the air, for example, if I have some kind of a ball and I throw it up into the air and it goes all the way up, we know when that ball is first leaves my hand, it's moving. If it's moving, it has kinetic energy, which is represented in this chart as E with a subscript K. And so I'm just going to say the ball has 1, 2, 3, 4 bars worth of kinetic energy, and that's where it's starting. Then what we do is we identify our system. Well, in this case, the system is the Earth and the ball going up into the air. So the little circle's the ball. And the direction of energy flow is from kinetic energy, or you can say the ball is going up in the air, that's the direction, or the direction of flow is from the chart on the left to the chart on the right. So the direction of energy flow is just saying what chart am I starting with and what chart am I ending with. Then we have to examine the types of energy that the ball has at the top. Well, let's say we see the following. What if we examined it and we saw that the ball at the top only had, maybe 3 bars worth of gravitational potential energy? That's the E with a subscript G, gravitational potential. Then you have to say to yourself, well, energy can't be created or destroyed, but it looks like, hey, we just lost a bar's worth of energy. So where did it go? And then you can start thinking about where are the places that I could lose energy. Well, I know that this ball, as it's going up into the air, it's got to hit a bunch of little air molecules on the way up. And as it hits them, all those air molecules begin to start moving around. They get hotter as a result. And so a lot of energy is lost, giving them kinetic energy and giving them thermal energy. And so what we're going to do is we're going to represent that as energy thermal, all of the heat gained by the air molecules, i.e. the energy lost due to air resistance. And so that little bar would go right there under thermal. And the reason being, we chose our system as the ball and the Earth. If we only chose our system as the ball, then we wouldn't have that little bar, and we would just say, well, the system lost energy because of that air resistance. So that's one example of throwing a ball up into the air. When you guys come into class tomorrow, on Monday, well, if you're doing this like a good student on Friday or Saturday, I guess in a few days. But when you come into class on Monday, we're going to start using these charts to examine really, really interesting and a variety of different situations. But for now, go ahead and please do the Google form quiz. to kind of test your understanding to make sure you got at least a decent idea of energy conservation, the thing we talked about here. There are solutions to each question, and it's not for a grade or anything. We're just going to use it to kind of guide our discussion to see where we're going to start on Monday. So, hope you enjoyed the video. I know I did. Have a great rest of your weekend, guys, and I will see you tomorrow or so.